Ever wondered how your computer manages to run multiple applications at once? It's like a digital juggling act, a magic trick that leaves you in awe. But what if I told you it's not magic, but a clever bit of technology that makes this possible? Yes, you heard it right. This seemingly magical ability of your computer is all down to something called virtual memory. Now you might be wondering, what is this virtual memory? Well, it's a fundamental concept in computing that allows your computer to use hard drive space as a sort of extension of its RAM. This in turn enables your computer to handle more processes than its physical memory would otherwise allow. It's a crucial player in the grand game of multitasking, allocating separate memory spaces to different processes, enhancing system responsiveness, and making efficient use of resources. Intrigued? Let's dive deeper into the world of virtual memory. Virtual memory, the unsung hero of your computer's multitasking abilities. This clever technology, born out of the necessity to handle multiple tasks simultaneously, is a fundamental part of modern operating systems. But what exactly is it? Virtual memory is a system that allows your computer to compensate for physical memory shortages by using a portion of your hard drive as an extension of the actual RAM. In essence, it's a bit like having a personal assistant who helps you manage your tasks when you're running out of hands. This brings us to the concept of virtual address space and physical address space. Imagine you're a chef in a bustling kitchen. The counter space where you're chopping vegetables and preparing dishes is your physical address space, the actual RAM installed in your system. But you've got more ingredients and dishes to prepare than you have space for on the counter. This is where your personal assistant, or your virtual address space, comes into play. They're keeping track of all the dishes you're working on, even those that can't fit on your counter, and making sure you have everything you need when you need it. The virtual address space is the larger contiguous space that programs use during execution, independent of the physical memory's actual layout. The operating system acts as the conductor of this symphony, managing the mappings between the virtual address spaces of processes and the physical memory. It uses a data structure called a page table to store these mappings. Each process has its own page table, which can be part of a hierarchical structure to efficiently manage large address spaces. In essence, virtual memory allows your computer to juggle more tasks than it could handle with just its physical memory. It's like having an extra set of hands in the kitchen, or an additional brain to help you remember all the things you need to do. Virtual memory, hence, serves as a bridge between the limited physical memory and the larger virtual address space. It's the unsung hero that keeps your computer running smoothly, even when it's under the pressure of heavy multitasking. Enter the art of swapping, the dance between your computer's RAM and disk storage. Imagine for a moment a grand ballroom. The dancers are the data packets, the dance floor is your computer's RAM, and the waiting area off to the side is your disk storage. As the dance goes on, some dancers tire out and step off the dance floor, while fresher, sprightlier dancers step in to keep the energy high. This is the essence of swapping, a fundamental aspect of virtual memory management. At the heart of swapping is the concept of page replacement. When the dance floor, or the RAM, gets too crowded, the operating system must decide which data packets or pages to move off the dance floor to the waiting area, or swap out to the disk storage. The goal is to keep the most relevant dancers on the floor, those that are actively engaged in the dance. Or in other words, the data that the system is currently using or will use in the near future. Now, how does the operating system decide who leaves the dance floor? This is where page replacement algorithms come into play. These are the rules that guide the decision-making process. The system could use a first-in, first-out approach, where the pages that have been in memory the longest are swapped out first. Or it could use the least recently used method, where the pages that haven't been accessed for a while are the first to go. There are several other algorithms as well, each with its own strengths and weaknesses, and the choice of algorithm can significantly impact system performance. Swapping is an essential mechanism that allows programs to use more memory than is physically available. It's like having an overflow area that ensures the dance can go on, even when the dance floor is full. However, it's not without its challenges. Swapping can cause delays, especially if the disk storage is much slower than the RAM. But when done right, it provides a seamless user experience, enabling smooth multitasking and efficient use of memory resources. Swapping is a delicate balancing act which, when done right, ensures smooth operation of your computer. So how does virtual memory work its magic? Great question. It all starts with a process called address translation. When a program needs to access memory, it doesn't use the physical memory address. Instead, it uses a virtual address, which is then translated into a physical address using a map stored in the page table. It's like using a GPS to find a location based on coordinates, rather than driving around aimlessly. Once the address is translated, the system checks if the needed data is already loaded in the random access memory, or RAM. If it is, great. This is what we call a page hit. But if it's not, we have a page fault. It's like reaching for a book on the shelf and realizing it's not there. Not to worry though, our system has a plan for that. When a page fault occurs, the operating system swings into action. It needs to load the requested data into the physical memory. But first, it must decide which data to evict to make room. Sort of like deciding which book to remove from a full shelf to make space for a new one. The decision of which data to remove is made using a page replacement algorithm. There are several page replacement algorithms that the operating system might use. These include the least recently used, or LRU, the first in first out, or FIFO, and the optimal page replacement algorithm. Each has its strengths and weaknesses and can impact the system's performance. It's like choosing the best method to organize your bookshelf by author, by genre, or by color. Once the operating system has decided which data to replace, it reads the needed page from the disk, loads it into the RAM, and then updates the page table. This is the swapping process, and it happens so quickly and seamlessly that we hardly notice it. And there you have it, the intricate dance of virtual memory, complete with its steps of address translation, memory access, handling page faults, and using page replacement algorithms. While it may seem complex, this intricate system works seamlessly in the background to keep your computer running smoothly. Like any superhero, virtual memory has its strengths and weaknesses. Let's start with its superpowers, the benefits. First off, virtual memory is a master of efficiency and cost-effectiveness. It allows a system to maximize the use of its physical memory, reducing the need for frequent and costly RAM upgrades. It's kind of like having a small but well-organized closet. You don't need more space, you just need to use it wisely. Next up, virtual memory boosts system stability. It's the unsung hero maintaining peace and order in your computer by keeping different applications' data separated in memory. This means that if one application has a hiccup, it won't cause a domino effect and bring down the others. It's the buffer zone that ensures one application's malfunction won't spoil the party for everyone else. The third advantage of virtual memory is flexibility. It's the gymnast of the computing world, bending and flexing to allow developers to design applications without having to worry about memory limitations. It's like having a canvas that expands as you paint, giving you all the space you need to create your masterpiece. And lastly, let's not forget multitasking. Virtual memory is the ultimate multitasker, juggling multiple processes at once by allocating separate virtual memory spaces to each. It's like having a personal assistant for each task, ensuring everything runs smoothly and concurrently. But like any superhero, virtual memory has its kryptonite. One of these is performance overhead. The process of swapping data between RAM and disk, known as paging, can cause delays. It's a bit like traffic congestion during rush hour. If the disk is significantly slower than RAM, the pace can slow down, causing a bit of a hold-up. Another challenge is the complexity in management. Efficiently managing virtual memory requires a sophisticated operating system with advanced capabilities in terms of memory handling and process scheduling. It's like conducting an orchestra. Every instrument has to be in tune and in time for the music to sound right. Despite its challenges, the benefits of virtual memory are undeniable, making it an integral part of modern computing. We've journeyed through the complex world of virtual memory, unraveling its mysteries. In this intriguing exploration, we've learned that virtual memory is an ingenious operating system concept that uses disk space to supplement physical RAM, enabling processes that require more memory than is physically available and facilitating multitasking. The crux of virtual memory relies on the intricate dance between the virtual address space, the physical address space, and the page table. This dance involves intricate steps of address translation, memory access, handling page faults, and the use of page replacement algorithms. The beauty of virtual memory lies in its ability to enhance system efficiency and stability, provide flexibility for developers, and enable concurrent execution of multiple processes. However, it's not without its challenges, as it introduces performance overhead and complexity in management. Next time you marvel at your computer's multitasking abilities, remember the unsung hero, virtual memory.